Hi, my name is Megan Sturm, and I'm going to be talking about my work diving into the inner disk of supermassive black holes with Hubble Space Telescope. I worked on this as a university scholar project with my advisor Jonathan Trump and Yasman Homayuni. So for our work, we were looking at accretion disk structure, specifically why there are discrepancies between this SS73 model predictions and some observations. We're using reverberation mapping, which is a technique that allows us to measure disk structure based on time lags. Essentially, the inner disk will exhibit flux variations in UV wavelengths, and then the outer disk will display the same pattern of variations but in optical wavelengths, and with some time lag corresponding to the extent of the disk. This is depicted in Figure 1. So our sample is drawn from the SDSS-RM project, which is a multi-object campaign targeting 850 quasars as part of SDSS-4. These targets have reliable masses and should be quite variable, but they also display a wide range of luminosity, redshift, and accretion rates, as shown in Figure 2, which help to clarify the cause of discrepancies between the SS73 model and observations. For our observations, we used HST-UV and coordinated ground-based optical monitoring. For one of the cycles of our HST observations, we used the drift and shift or dash observing mode due to our target's proximity in the sky. Essentially, HST used a guide star to acquire the first of our quasars, then drifted to observe the following four. While this saved time at each orbit, the targets had to be visually identified among cosmic rays in subexposures based on their less point-like flux distribution. In other words, they appeared blurrier and grayer. Also, the targets were smeared into different shapes due to the drifting. So to account for this, we performed aperture photometry using circular apertures of increasing radii, as seen in Figure 3, and we were able to successfully identify and make measurements for four of our targets. Once we made our flux measurements at each orbit, we were able to produce a light curve, Figure 4, for each of the wavelength bands that we observed. For these light curves, we see how the quasar is behaving over time and can calculate the time lag between the UV band and each of the optical bands. In the Figure 5, we are comparing our measured disk sizes with SS73 expectation, as shown by the red shaded region. Our disks probe a wide range of wavelengths in this rest frame, and we are currently working on fitting the disk normalization and temperature profile. We used SDSS-4 observations for this work. However, in the near future with SDSS-5 and its black hole mapper, the number of observed quasars will increase significantly and will permit both detailed reverberation mapping of specific quasars and statistical studies of a larger population. An interesting extension of our work would be investigating changing look quasars using the same techniques we use here. Changing look quasars vary dramatically in their accretion rates over a relatively short period of time. However, it's currently unclear how the accretion disk behaves during these changes. Performing reverberation mapping studies over the course of these changes could allow us to track the corresponding disk structure variability or invariability.